Okay, here's module 5, Eigenvalues and Eigenvectors. Um, so, why do we need linear algebra for ODEs? So here is a suggestive example. So I've got there a system that I've written in matrix form and also just in equation form. So if we look at the equations, we've got x1 prime equals x1. Well, the solution to that, is, of course, is just e to the t, and we can multiply that by any constant. We plug that back into the second equation, and we see that we have a linear equation. We know how to solve that. We just multiply by the integrating factor, which is e to the minus 2t. We then integrate that, and so we get minus a e to the minus t plus some constant b, and then we multiply through by e to the 2t to get x2 by itself. So we have that solution like there, and so we now write that back in matrix form as x equals a e to the t times 1 minus 1 plus b e to the 2t times the vector 0, 1. Okay, so we look at 1 and 2, and they've got associated vectors, and we see that 1 minus 1 is actually one eigenvector for that matrix, because you just do 1, 0, 1, 2 times 1 minus 1, and you get 1 minus 1. And 0, 1 is a 2 eigenvector. Again, you just do the matrix multiplication, you see you get 0, 2. It's just doubled. Okay, so this is kind of what we're going to do. We just got to, this was an easy example, but it just, all the other examples of systems can be solved in basically the same way. So the main little lemma, which is, which kind of shows that it works, that if you have an eigenpair for a matrix A, then x equals e to the rt times u, so e to the rt is a scalar, where r is the eigenvalue, times u is the eigenvector, is a solution to the system x prime equals ax. And the way we prove that is just by the normal verification. We just plug it in and check we have a true statement. So x prime is the derivative of e to the rt times u. And so when we take the derivative of e to the rt, we multiply by r. And on the right-hand side, when we act A on e rt times u, e to the rt comes out because it's a scalar. A times u, well, since u is an r eigen vector, that is just ru. Okay, so both actions of differentiating and acting by the matrix multiply u by r. Okay, and so this gives us a plan, right? So if we can find n eigenpairs, we can solve an n-dimensional system. And that sometimes works, but of course, if you're thinking a little bit, you can see, there's going to be problems. What happens if we've got complex eigenvalues? What happens if we've got not enough eigenvalues, etc.? Okay, but we can solve all that. First thing, how do we find eigenvalues? Well, here is the theorem from linear algebra that we need. So you've got a matrix M, and you've got a system of linear equations mx equals b, right? So x is a vector of unknowns, and b is some vector of knowns. Okay, this has a unique solution vector x for every choice of b, if and only if the determinant of m is unequal to 0, right? Because how do you solve mx equals b? Well, you let x equals m inverse times b. So you want m to have an inverse, and that's only true if the determinant is not 0. And so how do we actually go about doing this? So remember, we want to solve au equals ru. So if we turn that into a matrix equation, we put everything on one side, and we see that it's the matrix A minus Ri times the vector u equals 0. And this will only have a non-zero u as a solution only if the determinant of that matrix is 0. Okay, but the determinant of that is just going to be a polynomial in R. So if it's a n by n matrix, it's going to turn out to be a degree n polynomial in R. And that polynomial determinant of A minus Ri, that's called the characteristic polynomial of A. And its zeros are the eigenvalues of A. Okay. So let's pause here and we'll resume.